Well, thank you very much for the invitation. Thank you, Alicia, Nico, Ethan, and Oliver. I'm very happy to be here in Rio. And what I'm going to talk today is about this decomposition of tropical skeletons. Can you hear? It's okay, the volume? Okay. Maybe I have to put here linear, because I'm going to talk mostly of linear spaces, but some part of the work can be generalized to other situations. This is a work I've been discussing for a while with Erwan Brugale and Christine Shaw. Then even if this latest part wasn't exactly made with them, I have to talk about them. Then we're going to start by, the motivation of this talk was to approach the F-vector conjecture from another point of view. And the F-vector conjecture was announced by David Speyer. And it talks about the maximal number of I-dimensional faces that can have a linear space of dimension d in Tn. Okay, then if I have a linear space, LD, of dimension d, contained in Tn or Rn, as you want to. And you asked about the number of, since this is a polyhedral complex, you can ask of how many faces of each dimension they have. And for example, if we have like, we say that Fe of LD, I'm going to put here the n to keep it in mind, is equal to the number of I-dimensional faces of LD of dimension E. And you take the maximum between all the linear spaces of dimension d in Tn of this Fe LDN. And I'm going to call this number capital F N di. And David Speyer says that the conjecture says that Fn di is equal to, I'm going to copy is always equal to n minus 2I minus 1 d minus I times A minus I minus 1 I. This is the conjecture. And I'm going to call this number Speyer's bound NDI. Then, and all in his work, he approached this problem by matrix theory. And today I'm going to look at this problem with by tropical modifications. And in fact, what we're going to do is to change the problem that to count faces becomes to count connected components in the complement, or in the complement of a hyperplane arrangement. We can change this problem to count connected components in hyperplane arrangement. I forgot to tell here we have to put bounded. And here is also we have to count bounded components in hyperplane arrangement, in the complement of a hyperplane arrangement. And okay, we're going to start by looking at some linear spaces. For example, if we have n equal to 1 and d equal to 1, we have only this tropical linear space. N equal to 2, d equal to 1, we have this one or this one. Here, for example, we don't have bounded faces. Here we have only one zero-dimensional bound face, and here we don't have any one. And n equal to 3, d equal to 2. We have this, the tropical plane, I imagine you already know. And last example is n equal to 3 and d equal to 1. We have the skeleton of this hyperplane, or other generic line that is something like this. Okay? And here, for example, we see that the skeleton, I'm going to define now the skeleton, but it's the corner locus of this polyhedron complex is exactly a line like this. And if you look at this function in this one, you can see that here you're going to have only one zero-dimensional face. Here you have two. Here you don't have any one-dimensional face bounded, and here you have one. Okay? Then now we're going to see the skeletons. And well, I'm going to denote by SE of L is equal to the faces F face of L, such that dimension of F is at most I. Okay? And then, for example, if we want to count faces, bounded faces of dimension D, where D is the dimension of L. In fact, if we see at D minus 1 of L, the faces of dimension D are the complement in L of this set. We can see it as a complement of the skeleton, the faces. Okay? Okay, and then we're going to approach the tropical linear spaces by modifications. I have to define tropical modifications. And I'm going to talk only in this case, in the case of linear things. And the idea is the following one. If I have LD containing Tn, I can make n minus d steps to arrive to this linear tropical space from Td. I'm going to start with Td. I'm going to construct LD in D plus 1. I'm going to construct another, T2 of dimension n in D plus 2 until I arrive to LDN. N minus d. I'm going to construct from Td a series of linear spaces until I arrive to the space I want to study. Okay? And how are these? All these steps are called tropical modifications. And the idea of that modification is the following one. Here we have, for example, this line. I have T1. I'm going to consider a linear polynomial f from T1, defining T1. This is going to define a linear hyperplane in T1. And I'm going to consider the graph of the polynomial. It's going to be constant here and with slope 1 here. I hope it's clear for everybody. And this graph is not a tropical variety since it's not balanced. Thank you. And then I have to add infinite ray from this point with duration 0 minus 1 in order to have a linear, a line in T2. Then, for example, I arrive from this one to this one with a tropical modification. If I want to construct this one, I have to consider a monomial polynomial, and then we're not going to have this situation. We're going to have only the graph. For example, to construct this variety, we're going to consider the plane. In the plane, we consider the line defined by a linear polynomial. We consider the graph of this polynomial, and we have to add, for each point here, we have to add an infinity ray in the direction, and that's why we have these three other faces in the picture. Okay? I hope it's clear now. For example, to arrive to this one was in dimension 3. I start with this line. I take a polynomial who defines a zero-dimensional linear space, and I can perform the modification in order to arrive to this one. For example, coming back to this example, if I see a point in here, we're going to see that there's only one image, pre-image. I consider the modification is this projection. And if I consider a point that is not in the divisor defined by f, I'm going to have only one pre-image. And if I take a point in the divisor, I have an infinite number of possibilities, but there's one special, that is the higher one. You take the point, the point with higher coordinate here, and this is called the combinatorial lifting of P. Okay? For example, in this example, to construct this one, you will have here. For example, if I consider this line, the combinatorial lifting here will be exactly the skeleton. I will take one point, the point which is higher here, and then I have to add this h in order to make it balanced. Then what happened with the skeleton? I mean, in general, what we're going to have is we're going to have a linear space. Well, it's not very linear, but we have another linear space here of dimension, on codimension 1. And we're going to have the graph of this polynomial and one infinite ray in direction minus a, the last coordinate. And now if we want to see the skeletons, what happened with the skeleton? If I have here something that has its own skeleton, what is the skeleton upstairs? It's going to be the combinatorial lifting of the skeleton here with the corresponding new faces, and all union as a tropical cycles, the combinatorial lifting of the divisor. Okay, you're going to have, it's a very kind of miss. Well, maybe I can, well, it's exactly the picture I made here. But here we don't have any skeleton here, but the skeleton upstairs will be the combinatorial lifting of the line. Or here, for example, from this one to this one, we're going to have the skeleton here. We will have the combinatorial lifting of the skeleton here, and tropical sum with the combinatorial lifting of the divisor. Another thing we can see here in the modification is, for example, I'm going to, I don't know how to do it. Here. For example, when we make this construction, if we have a bounded face here, maybe given also by a piece of this polyhedral complex, when I go one floor upstairs, we're going to have that the number of connected bounded faces will be equal here and here, since everything we add was infinite trace. Then we can see, if we want to count faces, sometimes it's easier if we go downstairs and count and try to see what happened. Then this is why we're going to use modifications. We have a technique to follow what happened with the skeleton, and somehow a way to count the number of faces in each step, kind of. Okay? And for example, I'm going to make another example. And I'm going to modify again this tropical plane. Then the idea was to take a tropical line here, and make the modification. Then I'm not going to draw a four-dimensional picture, but I'm going to draw only a graph that has the same combinatorial type of the new skeleton. We're going to have something, the yellow one became something like this. This is not a point. And the purple one is going to be something like this. As you can see, each time I perform a modification, the skeleton is becoming more and more complicated. Okay? I mean, just here you can see that the skeletons are never, are not always linear spaces, but fortunately we have the following result. Is the main result of this talk. Is that this skeleton that becomes more and more complicated is in fact a linear spaces arrangement. What I mean is that I have Si of LDN is always a tropical sum of a sum of tropical cycles from G equal to 1 to K of linear spaces of dimension I in dimension N, where K is bounded by what I'm called, this is going to be S of D minus N minus D, D minus I. And what does this number means is I think they are called the polytopic simplicial numbers. I mean, for example, S to 2 is going to be in dimension 2 the number of points in a triangle of side 2, of 2 with 2 points in the side. For example, this number is 3. S 3, 2. This is the dimension, and this one is the number of points in a side. It's going to be equal to the number of points here, that is equal to 6. And so on. And the formula, in fact, is S is going to be equal to, I have the formula here, I think is S of AB is equal to a plus b minus 1b. It's always this number. Then here the number of linear spaces is always bounded by this number. And moreover, we have, as here, for example, in this example, we see that the skeleton of this one is only one linear, one line. But as I told you before, it's not a generic one. The skeleton of a plane in R3 is never of this type. It's at most of this one. Okay? Then the second part is that f I of L G, this is G, excuse me, Gin, is bounded by, not by the capital F of N, I, and I, but F is N minus D minus I. Then we can always decompose the skeleton as a tropical sum of linear spaces of the corresponding dimension. And we know that the F vector of these linear spaces is bounded by something. Okay? Yes. I mean, all depend on which number is this one. This one. This one. It means it's exactly this situation. Okay. What? Where? Here. It was the. It looked like a 4, right? Okay. Then this is the result. We can always decompose the skeleton in more simpler things that are linear spaces. And as a corollary of this, well, the theorem, the proof is exactly the thing I told you before with the modification. If I suppose it's true for a certain dimension, then I can decompose in some linear spaces. I perform a modification, and the new skeleton is going to be the combinatorial lifting of all these linear spaces and the new one. Then you can. The proof is following what I just said before. Then, as a corollary of this one, but also with this, okay, as a corollary, we have a bound of this number fi of LDN, because any I-dimensional face here will belong at least at one here. Then we know that this is bounded by k times f n minus d minus e. Then we can reduce the problem of this this F vector conjecture to the case when we are counting maximal dimensional faces. These two numbers are the same. Now, I bound something that I wanted to count I-dimensional faces in D and in a linear space of dimension n, D, in Tn. I bounded with something is count maximal dimensional faces. Okay? And then if we now have to look at this number, we know also, as a corollary of this one, that now we are taking, as I told you before, now we are taking the skeleton of the dimension 1 less. For example, for example, this one. This one is not very interesting case because this is always 1, because when equal to 0, this is always 1. But here you can see that we're going to have at least some number of points, some number of linear spaces. Here we have points. But also, if now we want to count maximal dimensional faces, I say in the beginning of the talk that we can think about these faces as the complement of the skeleton. Okay? The faces of maximal dimension are the complement of LD minus SD minus 1. Okay? But by this theorem, this one is a hyperplane arrangement. Okay? This is a hyperplane arrangement here. If I consider this one as my ambient space, I have a hyperplane arrangement, and I have to count number of connected components of hyperplane arrangement. Okay, then this theorem translates the problem in only look at maximal dimensional faces, and also reduce the problem of maximal dimensional faces to the case of count bounded connected components of complements of hyperplanes. Okay? And then now study hyperplane arrangement. What happened? For example, in the case when we are in Tn and we consider hyperplane, when LD is equal to this one, I consider a hyperplane arrangement. For example, this one. And I want to count number of bounded regions in the complement of this hyperplane arrangement. Okay? And it's an exercise to prove, that in fact, if I have classical one, here we have 4 tropical lines, and here we have 4 lines, classical one. The number of bounded faces here is the same. I mean, the number of bounded regions I can obtain with an arrangement is bounded ones are exactly bounded by the same number of the classical one. Okay? And the classical one, what is if I take classical bound of A hyperplanes in dimension B, is also a polytopic number. So as you can see here, 1 and 2 and 3, this is the triangle. This is SA minus BB. This is the bounds. And in the case of when LD is equal to TD, it's easy to prove that we have the same bound, because it's going to be the number of integer points in a certain polytop, integers and interior points in a certain polytop. And then you can find that this number is the same one. Well, now what happens if we are not in TD, we're in LD, in whatever, in another LD. For example, if I have a line and I take a hyperplane arrangement, for example, if I take 3 points, it's not the same. We don't have the same number of connected components of 3 different points in a line. But as in the case of classical ones, you can always think that this is going to be to count maximal number of faces in hyperplane arrangement. If you want to bound this number, you can consider the extreme case where everything goes transverse and everything is going. Then, for example, this one, I cannot recover 2 with 3 different points, but it's always at least 2. Okay, wherever 3 points you take in a line, you can consider that the number of bounded connected components is at most the classical bound. Okay? And for other cases, we can consider, since we have, if we want to prove this statement in a general situation, we can take a linear space. We can consider there a lot of linear spaces of codimension 1. We consider the maximal situation when everything is transverse. We have bounds for every number of bounded components of each dimension, and we can, since it's contractible, we can calculate the Euler characteristic and found the maximal number of faces. Then it means that F, what I wanted to say is that now we have this number is the number of connected components of this number of hyperplanes in dimension E, I. Then if we believe that the number I'm going to call now the tropical AB is the same thing, it's a hyperplanes in a space of dimension B. If this number is the same, then we have that this number here is always, this one was, I didn't write it, K was at least Sn minus D minus I. Then this number is going to be bounded by Sn minus D minus I. And this number is going to be bounded also by let me see where it is. And the other one is going to be Sn minus D minus I. We have this number of hyperplanes in this dimension. And if we write down the formulas, you have that this is equal to n minus I minus 1, D minus I, n minus D minus 1, D. And it turns out that this number is exactly the space bound for n, D, and I. Well, I have to say, anything I said now was with polynomials, then is for regular linear spaces. I forgot to say it. I never considered the case with the function to make the modification is rational. But for example, this works also. We have a tropical sum, then maybe there are something that is going to cancel it if you have negative numbers or you can maybe take away something. But this, to bound the number of regions, I always consider the case of polynomials, of linear polynomials and of rational ones. Then this result approach this conjecture and gives maybe an idea to try to prove the rest of the cases that are left with that is considered this rational function. Now we are only considering polynomials. But maybe we can extend the result in the case of rational ones. I mean, this for all these all the linear spaces that are obtained by polynomials are called regular ones, and the conjecture was already proved for these ones. This doesn't provide new cases in the conjecture, but the approach is different, and maybe we can just think about how to extend it for non-polynomial case. Okay, then this is the part of for linear spaces. And then what happened with nonlinear spaces? That we can again consider a theorem like this, where we have, for example, if I take one tropical variety, this doesn't admit any modification since we have this cycle. But we can, and it has its skeleton, and we can perform modification in this one. For example, following a polynomial define this line, we're going to have these 2 points, new points. And we're going to have a new curve that is like this. And again, we can decompose the same way the skeleton. We can consider this 4 point that we already have, and these new ones. And if I perform another modification, we're going to have another point, but we can always follow which point come from a modification and which points come from the skeleton of the minimal projection we can perform. Then to count again here in this one, bounded faces of a certain dimension becomes on count again connected components, bounded connected components of arrangement of not linear spaces, but another kind of varieties maybe. And I think they're in classical. There's already this kind of study. Not if you don't consider only linear spaces, but other kind of varieties. Well, everything I said until now was to bounded faces, and what happened with the case of unbounded faces. And for the rest of the talk, I want to explain why to count bounded faces in tropical geometry is enough to bound bounded faces in tropical geometry is enough to bound non-bounded faces too. For this one, I'm going to consider the tropical plane with this infinitum right here, and I'm going to consider a line in here. Every face in my tropical linear space that is not bounded goes to infinity and has an intersection with a face of maybe this one. And I think it's called the sedentary. Christian Carr is called the sedentary of a face is the dimension of the face of lower dimension that intersect an infinity. Then if I want to count these unbounded faces, I just have to look one dimension below, and I have a linear space, and I can count bounded faces in this infinitum face. Then, for example, if I have to count this one, I have to go to this corner, and here we're going to have 1 point, and you can count how many points. Then, for example, here we can found 3. We know we have 3 faces of dimension 1. We're going to have in each one 1 point, because it's a linear space of dimension 0 in T1. Then we're going to have 3 of them, and then it gives us the number of unbounded faces. In general, it's going to be the same. In general, I'm going to have, for example, in dimension 3, we're going to have something that goes to infinity in some sense. And I have to look at any face and count bounded faces in each face of this polyhedra. Then to bound, in general, to bound bounded faces of tropical varieties is enough to bound non-bounded faces. And as always, I finish earlier.